Welcome to final project of the CS449. In our project, we did throwing and catching robot, where one robot tries to throw and the other one tries to catch. So in our initial thoughts, it was just throwing the ball, and the catcher one was trying to catch with its gripper. However, after the implementation part, we thought that catching robot should not be in the same place and should change its space for ensuring the robustness and generic throwing and catching. So for the environment, we had a thrower robot which uses projectile motion and also some trajectory optimization model to calculate accurate throws, and we used randomized wing positions to test its robustness. And also we have a catching robot which detects and predicts ball trajectory using projectile motion to the points which are sampled continuously. And we integrated RRT for the dynamic repositioning. So we initially started with the normal throwing part, throwing to the bin. And then we made it to the generalized throwing so that it throws into different directions. Then we went to the RRT part plus the throwing. Here we can see that. And we are still trying to do throwing plus RRT plus catching, which is under revision. So in normal throwing part, we had a trajectory optimization methodology where we tried to find the release position of the ball along with the release velocity. Then with the COMO calculations, we created a motion plan for that. Then we executed them in BOTO. For generic throwing, we also incorporated for initial position of the throwing state, we've also incorporated the links orientation to the ground and itself as well. And we've managed to have a successful generic trajectory throwing, which have a success over 50%. The throwing has a range of 2 meters. And for 1 and 1.5 meters range, the accuracy increases. However, after that, the accuracy decreases after the distance increased. Accuracy rate of the normal throwing is tested on thrower tests. We observed that the normal throwing is not generic, and how we did that is that we generated 100 different samples from the range of the throwing, and we checked whether for each one the throwing is successful or not, and we had a deviation scores as well. With 100 terms, we found out that there were only 12 points which are successful, and this was not generic. After the progress report, we created some tests, and the throwing is increased more a lot. So as we can see, from 12% to 50% accuracy is achieved. How did we do that? Is that we've just created thrower test and generated sample points, 100 sample points randomly, and for each one we checked it like that, whether it is a success or not, and we've written it on these JSON files.
For this project, we also wanted to make it more generic so that it can be used in other scenarios. And a common issue for this is that the robots could be too close together, resulting in collisions, or they could be too far from each other, in which case the ball wouldn't be able to reach the target area, and this can be solved by using RRT path planning, which basically moves the throw robot closer to the catcher robot, and in such a way that we achieve an optimal thrower positioning in which we have maximum success rates. So for example, you can see over here the robot is impeded by the walls over here, and it wouldn't have been able to throw the ball as it would have hit the walls. So it moves to an optimal throw location and then throws the ball to achieve high success rate. This is done in the code by first checking if the robot is obstructed. This is to make sure we are in the optimal location or not. If we're not in the optimal location, there's a method that moves it closer, and it's based on the throw radius and the maximum throw range radius. And as soon as this is close enough for the catcher robot, we can calculate the throwing trajectory and make successful throws.
We move on to the catching part. Along with the throwing and RRT part, our goal was to enable the catcher robot to track and catch objects in midair. We only use a ball to try this. Our key tasks was to implement a catcher robot for trajectory prediction with projectile motion for trajectory prediction and with continuous sampling. And then we synchronize the throwing and catching operations together. The hardest challenge for us is to ensure accuracy in trajectory prediction and interception timing. This is our catcher robot class. Here we have created two threads in order not to make the thrower and the catcher robot wait for each other, because since the thrower will throw the ball and the catcher needs to make adjustments from where it's going to catch. We always update the prediction of where the ball will land, like the velocity predictions and the landing point prediction, which is just approximately 1 meter apart from the robot at most. And then we executed the movement. The predict catch position is done by projectile motion. Like we only calculated the X, Y, and Z positions of the ball that will be according to time. And how we estimated velocity is by taking samples, as I said before. Like we always compare the most recent two samples to take the velocity because it's always changing. And then we have moved gripper to the position, of course, the bin position with comma. And we also used a physics engine for that, and we needed to use a really high numbers for the physics engine in order to make the catcher robots be quicker, because we had a really big issue with the timing. And I need to mention that I just used the thrower generic parts that the Tuna has wrote. I just integrated them together and added callbacks.